So thank you to Professor Riddhi Shah for inviting me to this workshop. I would have been happier if I could come for the whole week, but because of, we are all in teaching institutes and we cannot we have other responsibilities, so I could manage to come only for a kind of 1.5 days. But it's a great pleasure coming here because after coming here, I realized that all the faculty members, math faculty members in your department are my friends or have been my friends. So it's good to see all of them. So thank you very much. So now all of you are listening the lectures by Athanas, and today morning also Athanas was talking about marked hyperbolic structure and hyperbolic structure on surfaces, right? Yeah. So how many of you have seen that? All of you, right? So all of you know what is Teichmuller space by this time. Yeah. So what I will do, I will start with a kind of orientable surface of genus G, and you can have on kind of P boundary components. So I consider boundary components as punctures. Okay. So then what is the Euler characteristic of the surface? Have you seen that? No. So that is 2 minus 2g minus p, and you take it less than of negative Euler characteristic. Because unless you take a surface with negative Euler characteristic, you will not have hyperbolic structure there. Okay. So now you look at the universal cover of the surface. Because I think you also had a course on homotopy and universal cover that Professor Riddhi Shah has lectured, right? So what is the universal cover of a orientable surface of genus G? So this is topologically, these are facts, okay? I mean, you can look at the book by Massey, Algebraic Topology. So some of these stuffs are there, okay? So there is a chapter on classification of surfaces, and the universal cover plays a crucial role there. So this is topologically a disk, okay? And pi 1 sigma, the fundamental group, so this acts on sigma tilde by deck transformations. Fine? Yeah. So now, okay, so I am using a bad notation. So this is the kind of projection map. Projection. You should not confuse it with the fundamental group. This is projection. Okay, I mean, I can call it some other notation also. Maybe call it P. Okay, if you want. Okay. Then P of, say, so you take P1, P2 in sigma tilde, then P of, again, I mean, bad notation, so I think I change it by something, maybe C1, C2, okay. So P of C1 equal to P of C2, if and only if, what would be the condition? C1 should be a translate of C2 for some alpha in the fundamental group. It follows from basic covering space theory. So that means if you take a action of the fundamental group of the universal cover, then the orbits, okay, the orbits kind of gives you a map from the orbit space to the surface, right? So you have a map from sigma tilde mod pi 1 sigma to sigma, and you know, right, that this is actually kind of a homeomorphism. So and every kind of surface arise in this way. Yeah, these are this follows from basic covering space theory. Okay. So now in Athanas's lectures, you have seen this space, hyperbolic plane, right? He has lectured. So which models he has discussed? The upper up space, yeah, the complex upper up space. Okay. So this is, and this is the boundary, yeah. And what is isometric group of hyperbolic space? That is, no, this is PGL2R. Okay. So the orientation preserving isometries is PSL2R. Otherwise, the full group of isometries has two components, one orientation preserving and orientation reversing. Okay. So now you consider, I consider G to be, I mean, let's look at only the orientation preserving component. Okay. Consider G to be PSL2R, okay, not PSL2R, consider G to be SL2R, the matrix group, or SU1, 1, or SO2, 1. What is the relation between these three groups? They are all isometric groups of different models of the hyperbolic plane. So the first one is for the upper up space, the second one is for the ball model, and the third one is the linear model or the conformal model. I mean, it's a kind of Lorentzian model, you know, like you have a bilinear form of signature 2, 1, and you, I mean, yeah, I think if you don't have seen this, then if I have time, I will discuss this model in more detail. But these are all models of the hyperbolic plane. Okay. So now a representation rho from the fundamental group to this group G is just a group homomorphism. Okay. So now you consider Hom pi 1 G, the set of representations of pi 1 to G. So the group G acts on Hom pi 1 G by conjugation. Okay. So we are interested. Okay. So this I think let's not talk about this now. Let's first let's not talk about this at the moment. Okay. So this is a set that I had defined. Now you consider a map F from sigma tilde to H2. This is kind of equivariant. This is rho equivariant if F rho alpha is rho alpha Fp for all p in the universal cover and alpha in pi 1. Okay. Now, so you now have a kind of rho equivariant family of maps, and you kind of you have this set of representations of pi 1 to G, where G acts on itself by conjugation, and you have the conjugation orbits. Now, what is the correspondence between these two? So, there is a close correspondence, and these two objects give you a correspondence between the topology, geometry, and algebra of the representations. So, the correspondence goes like this. So you have a correspondence between Drake transformation, hyperbolic isometries, and matrices in SL2R. And then you have a kind of you have a correspondence between equivariant maps and action by by representations of the fundamental group into gamma. Okay, and then how this correspondence is built? So that is, let me just briefly tell you. Okay, so let me change my slides. So now, to give an indication how this correspondence is built, you recall what was a marked hyperbolic structure that Athanas has talked about in the morning. So a marked hyperbolic structure on sigma. So how he defined? Can anyone remind me? A homeomorphism. So I call it a pair M1F, okay, where M is a hyperbolic surface and F, well, I am not considering it as a homeomorphism at the moment. You can consider it as a homeomorphism, but you can consider also is as a homotopy equivalence. Yeah, so this will essentially give you the same thing. And you have two hyperbolic structures, so call them F sigma to M and F prime sigma to M prime are equivalent if there exists an isometry M to M prime. So now, when I am talking about isometry, I am giving them a metric coming from the universal cover, which is the hyperbolic plane. So there is an isometry such that this diagram kind of homotopy commutes. So you have F, you have F prime and this. So this is homotopy. So that is phi compose F is homotopic to F prime. Okay. So now what happened that you have every equivalence class of marked hyperbolic structure. Corresponding to that, you have this you have discrete groups. Okay, and those discrete groups are conjugate to each other, because as soon as you have a, or if you consider them as a homeomorphism, like somebody pointed out, maybe it will be easier to understand homeomorphism, then from the universal cover, every such hyperbolic structure is coming from a discrete subgroup of PSL2R. Now, two structures are equivalent, that means the discrete subgroups are conjugate to each other. So, to every equivalence class of marked hyperbolic structures, there is a well-defined equivalence class rho in home pi g mod, okay, it's called home pi g mod G. So this is the kind of conjugation orbits. Okay. So corresponding to every hyperbolic structure, there is a conjugation orbit of representations. and a representation rho pi 1 to g is called Fuchsian if it comes from a hyperbolic structure. Okay. So, equivalently, a Fuchsian representation satisfies three conditions. So, the first condition, rho is injective. That means the representation is faithful. Second condition, image of rho is discrete in G. So, this is a Fuchsian group. And the third condition, rho is type preserving. What does it mean? That means rho of alpha if it so type preserving means you have these loops, right? So, if the loop is a closed loop, then it corresponds to a hyperbolic element in the isometric group. So, rho of alpha has to be hyperbolic, and if it is near a puncture, then it is a kind of cusp. So, rho of alpha will be parabolic element. Okay, so that is called type preserving representations. Equivalently, this means yeah. So, let us not write type preserving if it is kind of, but they are the equivalent conditions here. So, equivalently, G mod not G mod rho gamma, equivalently yeah, G mod yeah, equivalently what? So, equivalently rho of pi 1 is geometrically finite. That is, it has a finite sided so you know what is the fundamental domain? Anyone does not know what is the fundamental domain? Was it discussed in this course? No. So then I think type preserving is better. So type preserving means
it was mentioned once, but
okay. So but anyway, so that means in other words, rho is type preserving. That means it maps hyperbolic loops onto a hyperbolic elements and cusps to parabolic elements. And rho cannot, yeah, so pi 1 is a fundamental group of a surface, right? So it can have only two kind of loops. Either the loops is homotopic to a closed curve or the loop is a cusp. So if it is a closed curve, the image is hyperbolic element. If it is a cusp, the image is parabolic element. That's what type preserving means. Okay. So these are the three conditions that a Fuchsian representation satisfies. And this is one realization of the Teichmuller space that you were looking at. So this gives one realization of the Teichmuller space as one of the component of Hom pi 1 sigma PSL2R mod PSL2R. That contains the discrete faithful type preserving representations. So this space home pi1 PSL2R mod PSL2R, this is a space, and this space is a disconnected space. It has several components. Now one of the component consists of all discrete faithful type preserving representation. That component can be identified with the space of all hyperbolic equivalence classes of hyperbolic structure on the surface, which is the Teismuller space that we have seen. So yes. It's a topological space, so it has disconnected space, so it has connected components. So one of the component is Teismuller space, and it consists of all discrete faithful type preserving representation. So this space has many other components also, and yeah, so this is a kind of space that is this whole space has not kind of been completely well understood till date. But Teismuller space, I mean, there has been a lot of development that you are already, some of the developments you are already seeing, right? Okay. So
Do we have any information about other component, at least one?
yeah. So you know, there is another component that consists of discrete faithful type preserving orientation reversing representation. That means there is if you give a orientation, then another this is the orientation preserving representation. There is the orientation reversing representation that looks just like the Teismuller space. Now there are I think in between there are 3G minus 3 components. Okay, and how each of the components behave, I don't know. Okay, so that how many components are there in this space, that is also a kind of deep problem. And there are works by William Goldman who understood it to some extent. Now this correspondence between you know this thing, the correspondence between Fuchsian representation and hyperbolic structure, etc. These follow from classical work of Fricke, Klein, and Andre Weil. So yeah, so I will Klein groups, yeah, Kleinian group, yeah. So there, you know, you take so more generally. That was my next thing. More general, I am taking a slight digression here. More generally, you take any Lie group. If you don't know Lie group, you don't worry. Take matrix group, any matrix group, yeah, any linear matrix group. Then GLNR, yeah, subgroup of GLNC, closed subgroup of GLNC. Okay, then home pi1G, you can consider it, you know, there is a map from home pi1G to G to the power n, where n is number of generators of pi1, the fundamental group of a surface. Okay. So what you do, you take rho and then you map it to rho gamma 1, rho gamma n. So this way, this space can be considered as a subspace of G to the power n. Now this is a Lie group, so it has a nice smooth structure. So home pi1G can be considered as a subspace of G to the power n. And from there you can get the topology, but smoothness needs to be verified, right? You know, right, that subspace of a smooth manifold may not be always smooth, that you know, right? So it may not be smooth, but it has a nice topological structure. And if G is a algebraic group, then this space home pi 1 G is an algebraic subset of G to the power n. So, if G is the algebraic group, that means if you can think of G as a 0 set of some polynomial, then home pi 1 G is the algebraic subset of G to the power n, and you can also view it as a algebraic object. Okay. So, now the point is this group, automorphism group of the fundamental group times automorphism group of G, that has a natural action on home pi 1 G, and the action is given by rho alpha. So, how the action goes, you take sorry phi, you call it phi, okay, phi alpha, you take a element rho from home pi 1 G, then this goes to alpha compose rho compose phi inverse. This is a natural action. Yeah. So, in particular, if you consider alpha kind of to be identity, okay, then you have a nice quotient, right. So, mostly G is any Lie group, or yeah. So, mostly the quotient home pi 1 G mod pi 1 G, which is the representation modulo identity times inner automorphism of G. So, this is same as representations up to conjugacy. So, when you take inner automorphism, it is just the conjugation action. So, it means you take the conjugation action of G on this representation space and you consider the conjugation orbits of all this representation. So, that is this space. Okay. So, this space is of much interest, and depending on the Lie group G, the understanding of this space changes. So, in the previous few minutes, I discussed only this case when G equal to PSL2R, which is the Teichmuller space. But if you change your Lie group, your understanding of the so this space sometimes is known as a deformation space of a representation. So, this deformation space changes, and the geometry, topology and algebra of this space can be very different from the low dimensional case. Okay. So, nowadays I think there is a kind of it's a kind of trend, modern trend to look at the spaces when G equal to SLNR or when G equal to SLNC. So, there are analog of Teichmuller space in these setups. So, there is also a nice space of nice ball of certain dimension, and there is a kind of a lot of research is going on in this direction. But that is not the aim for me, that is not the aim of my lecture in this short time. Okay. So, what I want to do, I want to consider another group, which is the group of isometries of the complex hyperbolic space. Okay. So, but before that, I just want to give you one information, that whatever I said, like description of this space in general, or a kind of proof of all these correspondence. Okay. So, you can much of it you can look at. So, there is a book by M.S. Raghunathan called Discrete Subgroups of Lie Groups. So, he has a chapter, Discrete Subgroups of Lie Groups. So, a general discussion about these spaces can be found there. Chapter 6. Yes. So the general discussion can be fine. So this is related to some old work by Andre Weil, and he essentially kind of discussed that result. Yeah, yeah, but his approach is more general. So you get a general feeling about these objects. But if you want to look at the real geometric structure, then it depends on the target group that you are taking. Okay. Any questions so far? Yeah.
In the afternoon talk, we saw that equivalent space as a subset of this space, the length functions. Is that similar to what we discussed?
So that's a very kind of nice information when when the target group is PSL2R. Okay. One reason is the following. So this group gamma, you take a discrete subgroup of PSL2R. Okay, and the surface he was talking, those are compact surface without punctures, right? Or with punctures? Without punctures. So if you take surface without punctures, then you don't need this condition. The only condition is that rho of alpha is loxodromic element or hyperbolic element. Okay. So now that means you take this discrete subgroup, which is called a totally loxodromic subgroup. That means all elements are hyperbolic. Then in PSL2R, what happened? The hyperbolic elements are conjugate to R inverse. You know that, or you don't know? That has not been taught. Okay. Okay, so I will give you a brief thing about that. Okay, so let's take a digression because this question has arisen. So we are talking about, this is also relevant to what we are doing. We are talking about PSL2R, right? So these are the isometric group of the hyperbolic space, which is like a unit disk. Yeah, unit disk. Now you can check. And the group action is Z goes to AZ plus B by CZ plus D. Yeah, AD minus BC equal to 1. F. Now if you consider fixed points of F, how many fixed points it can have? It can have at most 2 fixed points. Yeah. So F can have at most 2 fixed points. So it is called elliptic if F has a fixed point on D2. It is called, and if this action also extends to the boundary circle, so the fixed point can lie either inside the disk or in the boundary. Now suppose it has no fixed point inside the disk. Okay, then how many fixed points it can have on the boundary? It can have at most 2 fixed points. Okay, the reason is the following. Suppose it has another fixed point. Yeah, then you join these 2 fixed points by a geodesic, and then you join maybe so then what happened? You join these 2 fixed points by a geodesic, and so there is another geodesic that join these 2. I mean, so you get a triangle, right? And the center of mass of the triangle, that has to be equidistant to everything. So it has to fix another point in the well, I mean, I'm drawing a wrong picture here, but anyway. So the picture has been messed up. So, but anyway, no problem. So D2 bar. So this is so if it has 1 fixed point inside the it has 3 fixed points on the boundary, then it fixes everything. You can also see it in a concrete way. So like if it has 3 fixed points, then using cross ratio you can prove that it fixes everything. So if it is not elliptic, it can have at most 2 fixed points on the boundary. It is called hyperbolic if F has 2 fixed points on S1. It is called parabolic if F has unique fixed point on S1. Okay, and this is a trichotomy. There cannot be any other type of isometry or any other type of Mobius transformation of the unit disk. So now, so do you know this result that PSL2R acts transitively on isometry group and doubly transitively on the boundary? You know, don't know. Okay. So what happened that this isometry group, if you take any 2 points inside the disk, you can always find one isometry that maps P to Q. So this is called transitive action. So PSL2R acts transitively on the unit disk. And on the other hand, on the boundary, if you take 2 points, P1 and Q1 and P2 and Q2, you always get one element from PSL2R that maps P1 to P2 and Q1 to Q2. So that's a kind of remarkable property. Using this property, up to conjugacy, you can always assume that if something if something fixes 2 points on the boundary, then those points are 0 and infinity in that upper half space model. Okay. So up to conjugacy, you can have elliptic transformation as this form. So this requires some proof which I am skipping. Parabolic transformation are just upper triangular matrices, and hyperbolic transformation are diagonal element of this form. Okay, up to conjugacy. Fine. And this is if and only if trace of a element is always less than 2. This is if and only if the trace of the underlying matrix is always 2, and this is if and only if trace of A is greater than 2. So this way you can even detect the types of the isometries algebraically using conjugacy invariance like trace. Fine. So now if you have a hyperbolic isometry, okay, so it fixes 0 and infinity. So you have so let us talk about upper half space model. So this is, for example, a geodesic joining 0 and infinity, right? So this geodesic projects to a closed geodesic in the fundamental group, and you can talk about its length. Okay, so that's how the length appears in the correspondence that you are mentioning. But in higher dimension, the situation is not so simple, because there may be more kind of geometric invariance that can associate with, because you are no more in a 2 by, so essentially the length of a geodesic, is the trace in dimension 2. So this length can be expressed in terms of trace. Okay, but in higher dimension, if you take conjugacy invariance of a matrix, there can be more conjugacy invariance. But yes, some analogous study can be made, that how you can relate one this deformation space or the higher dimensional Tetzmuller space with length type kind of tuple. Yeah, that can be made. Have I answered your question? Okay. Okay. So anything else you want to ask? Okay, fine. So now I think I am almost kind of near to the end of my talk. So how much time I have? 1 hour? Yeah, 5:30, right? Yeah, 5:30. Okay, so 10 minutes. So I will briefly tell you what is this object called complex hyperbolic quasi-Fuchsian spaces. Any questions so far? Okay. So we talked about Fuchsian representation when you have G equal to PSL2R and you take the discrete faithful type preserving representation into PSL2R. Now you replace G by SU2, 1. So what I will do, I will SU2, 1. Okay. So at the moment, I will not tell you what is this group, except what is this group U2, 1. So this is group of 3 by 3 matrices such that they satisfy this condition, okay, where J is -1 0 0 0 1 0 0 0 1. Just take it. And what is the significance of this matrix? I will come back, but after telling you what are the main objects of my title, because otherwise I will not have time to say that. So the Fuchsian representations were discrete faithful type preserving representation into PSL2R. Now a complex hyperbolic quasi-Fuchsian, a complex hyperbolic quasi-Fuchsian representation is a representation rho from pi 1 sigma to SU2, 1 such that rho is injective like before, image of rho is discrete, rho is type preserving, okay, and then rho is geometrically finite. So for discrete subgroups of PSL2R, type preserving automatically implies geometric finiteness, but for SU2, 1 it does not. So we have to add this condition. So all discrete faithful type preserving geometric representations are called complex hyperbolic quasi-Fuchsian representation, and the space of all such representation, or their image is called a complex hyperbolic quasi-Fuchsian group, and the space of all such representation is called complex hyperbolic quasi-Fuchsian space. Okay. So QC, okay, so QC sigma is a subset of Hom pi 1 sigma SU2, 1 modulo SU2, 1 consists of these representations. So now question, for Fuchsian representation, we know, right, how these representations are sitting inside this space. We know it's a connected component. Now the question is how to understand this space. Even though there are many works in this direction, but in general this space is extremely hard and not much is known about this space. So any result that you can ask for Teichmuller space can be asked for this space as well, and most of the answers are not known. For example, how this space is sitting inside this representation space, or one big question is, I mean, this set is a subset of this space, right? How the boundary of this space looks like. So there is no understanding of, even it is not known whether this space is connected or disconnected inside that space. Okay, so this is a kind of wide open kind of generalization of the classical Teichmuller space from this viewpoint, and nothing is known. Okay, fine. So there are many problems associated to this, and there are some people who have worked on this problem also. So still a lot of, I mean, one needs to develop some machinery to understand these spaces, which is still not known. Okay, though a lot of work has gone into this picture, and many people have used computer experiments to understand many aspects of this space, but still most of the questions are not known. So it's a kind of wide open object, but very difficult object, I would say. Fine. But nevertheless, I think since we are discussing this space, I have not told you what is SU2, 1 and how it is related to hyperbolic geometry. So let me just quickly recall what is a complex hyperbolic space. So you have seen about hyperbolic plane, right? So this complex hyperbolic plane is the complex analog of real hyperbolic plane. And so let's do one thing. Let's take a field R or C. Okay, take a vector space, three-dimensional vector space over F, and give this vector space this bilinear form: Z1 W1 bar plus Z2 W2 bar minus Z3 W3 bar, right? So this is a non-degenerate bilinear form. In case of real, it is a bilinear form. In case of complex, it's a Hermitian form. Now one can also give a equivalent Hermitian form, which I denote by ZW2, that is Z1 W3 bar plus Z2 W2 bar plus Z3 W1 bar. So you know when two Hermitian forms are equivalent, right? That means this Hermitian form, it is Z J W bar star, right? Where J is 1, 1, minus 1, and this is Z J2 W bar star, where J2 is 0, 0, 1, 0, 1, 0, 1, 0, 0. So you know, right, every Hermitian form can be represented by a matrix, right? So equivalence means these two matrices are sort of equivalent. That means bar, of course, bar, yeah. No, if you don't take bar, then oh, I see, I understand what you are saying. Okay, it's a kind of notation, yeah. A star, okay, star, yeah. Okay, fine. Transpose, yeah. Okay. So if you take this matrix C, which is 1 by 2, 0, 1 by 2, 0, 1, 0, 1 by 2, 0, minus 1 by 2, then C J1 C inverse is J2. So that means these two Hermitian forms are equivalent to each other. Okay. So there are many other Hermitian forms that you can take, but let me quickly define the complex hyperbolic space. So now this, so let's talk about the first Hermitian form or the second, whatever. This decompose this space into three disjoint subsets. You collect the vector of the same sign, and also you have a set which is a collection of vectors of length 0. So this whole vector space V, this is a disjoint union of V naught, V plus and V minus. So now in topology or linear algebra, you know that you can consider the set of all lines and define a projective space. Yeah. So P is a map from V minus 0 to the projective space. Yeah. So now linear algebraically, the hyperbolic plane over F is the image of V minus under this map, and the boundary is P of V naught. Very abstract definition. So I am just considering the projective image of the vectors of negative length as the two-dimensional hyperbolic plane, where F can be real, F can be complex, does not matter. Now how you are recovering the usual way of the usual hyperbolic space. Let me just tell you that. So what happened? What are the vectors of V? Z1, Z2, Z3, right? And when you are taking them in the projective space, it is well defined up to a scaling. Now, because of this condition that ZZ less than 0, what do you have? You have mod Z1 square plus mod Z2 square minus mod Z3 square less than 0. So, Z3 cannot be 0. It is always non-zero. So, you can scale that and you can take this representative of the same vector. Okay. So, now if you call it W1, W2, 1, then plugging into this relation, this gives you W1 square plus W square 1 minus 1 less than 0. So, that means this space PV minus that has a 1-to-1 correspondence with all two tuples of vector such that W1 square plus W2 square is less than 1. What is this when W1 and W2 are real number? This is the unit disk or unit ball, right? So, that gives you the ball model of the hyperbolic plane. And when f is a complex number, this gives you a 4-dimensional ball, which is a model for the complex hyperbolic plane. Okay. And using the other Hermitian form also, you can get a kind of nice model. I would end here that whenever you talk about hyperbolic plane, there is a metric associated to this. Now, what is that metric? So, that metric in this setup is called a Bergman metric, and it can be defined in the following way. So, you have two kind of so you have 2 points Z and W in the complex hyperbolic or real hyperbolic plane. You leave them to F3, okay, and then you have the inner product there. So, in terms of inner product, you can define this in this same way, in this way, okay. So, this will give you the normal hyperbolic metric that you are talking about. Fine. So, this gives you a model for the complex hyperbolic plane or the real hyperbolic plane. And you started with this bilinear form, this one. Now, in linear algebra, take set of all matrices which preserve this Hermitian form. So, that matrix is precisely U2, 1, because this satisfies this J, Z, J, W star. So, any matrix that satisfies A, J, A star equal to J, that means which preserve this Hermitian form, consider the set of all such matrices as U2, 1 in the complex case. In the real case, that is denoted by O2, 1. And that gives you the isometric group of the corresponding model of the real or the complex hyperbolic space. So, in the complex case, we normalize them and take the determinant 1 matrices. In the real case, also you can take SO2, 1, but you have to be careful because in the real case, SO2, 1 is a disconnected group. So, you take the connected component of that group which preserves the hyperboloid ball. Okay. So, this way you can connect linear algebra and hyperbolic geometry. So, there are some more, the kind of classification that I have given, elliptic, parabolic, hyperbolic, that also holds true for SU2, 1 as well. And the type preserving representation accordingly can be defined similarly. Okay. So, I think with this I would like to stop here. So, I have tried to give you a gentle introduction to complex hyperbolic space and the deformation theory of discrete subgroups into the isometric group of the hyperbolic planes. So, one of the theory you are already seeing since the last 1 week, probably without realizing that it can be interpreted in the same way. Now, one kind of good problem would be to generalize some of those results in the complex hyperbolic setup. So, thank you. I think, yeah, thank you.